In part 1, we laid the foundation for recreating the ZX spectrum using TTL logic and EPROMs. Now, it's time to dive into the next vital part of the machine, the memory system.
Sweet dreams are made of these.
Memory isn't just a place to store data, it's the canvas where computing unfolds, a critical component that shapes how the CPU interacts with programs and graphics. In this episode, we'll go over the memory required to form a Turing machine in the first place, then break down how the ZX Spectrum's memory is structured, how the finite state machine accesses it, and why understanding the memory is key to building a fully functional system from scratch. By the end of this part, you'll see how memory and logic come together to recreate the magic of Clive Sinclair's iconic machine. Let's get started. In the last video in this series, I built a finite state machine which was really two machines in one, but in this video, I want to focus on the Z80 side of things. In its simplest form, a finite state machine has some combinatorial logic, which I generally encode with an EPROM, although this isn't strictly necessary. It's just one of the easiest ways to implement complex logic. A state machine has state, which is the data stored inside the flip-flops, and this state feeds back to the combinatorial logic. A simple example of a finite state machine is an up counter, which I've shown up the top here. The input to the EPROM is the number n, and stored at location n is the number n plus 1 ANDed with FF, to keep it within the 8-bit range. On every positive edge of clock, we count up by 1 until we hit 255 in binary, then we roll over to 0. This machine has 256 states, where each state is a number between 0 and 255, hence, it's a finite number of states. Now, it's also possible to make up a counter with a binary adder in place of the EPROM, which is what I've shown in the middle here. It works the same, but obviously the EPROM is much easier to change, say to count in binary coded decimal, which would require extra logic with the adder-based circuit. Okay, this is the simplest form of a finite state machine, but we can add more outputs if we want. In the case of the Starman raster generator example, we added an output port which contained HSync, VSync, and 8 bits of color. Technically, I used 19 bits of state for VGA even though I've only shown 16 here, but hopefully you get the idea. I've expanded the finite state machine to include output, but a finite state machine can also take information in from the outside world through the input bus, which feeds into the combinatorial logic, in this case, the EPROM. What this means is that for our EPROM, we have an entry for every possible state and every possible input for each possible state. I'm going to call this input the data input, but this is just a name change rather than a functional change. We're getting closer to what we need, but now I'm going to subdivide the output into some regular outputs and the data output. But again, this is really just a name change. It's all output. So, how does this relate to the machine Turing defined? Well, although Turing didn't use the term state machine, this is part of what he described in the paper, and what he referred to as the machine's configuration, we call state. And there's a finite number of configurations. The next thing Turing added was a tape. He didn't specifically say it was a magnetic tape, but that's a fair interpretation. In theory, this tape has an infinite length, but think of it as being as long as necessary. We convert one of the outputs from the state machine to be a left-right bar signal, which controls how the tape moves. Okay, let's look at an entire clock cycle. The read-write head is connected to the data input on the EPROM. When clock's low, we read the data from the tape, which in this case is the character Z. Now let's say the combination of the current state and the Z input gives us a new state and an output of N. The data output's also connected to this bus, and we use the output enable signal to make sure that the output only occurs while clock's high. In this case, N is transferred to the tape. On the falling edge of clock, the tape moves based on the left-right bar output. In this build, I don't want to use a magnetic tape, and I would argue that this up-down counter connected to a static RAM is the solid-state equivalent of a one-dimensional tape. The up-down counter on the address lines into the static RAM effectively converts it from a static random access memory into a static sequential access memory. Let's say we can make this up-down counter and static RAM as large as we want. I'll call it n bits wide, where n is some large number, even up to infinity. I would argue that this is a solid-state replica of the machine described in Turing's 1936 paper. In fact, I'd encourage you to download a copy of the paper and just read the first 3 pages. See if you come to the same conclusion. Why is this important? Well, we have this concept called the Church-Turing thesis. The Church-Turing thesis states that a Turing machine is the most powerful computing machine possible, and it's possible for a Turing machine to emulate any other Turing machine. When this occurs, the machine's called a universal Turing machine, and it's the most powerful computing machine known. It turns out that the Church-Turing thesis hasn't been proven, but in nearly 90 years, no one's been able to disprove it. Somewhat ironically, if you were able to disprove it, you'd win the Turing Award. According to this thesis, this machine can emulate any other known machine, including the ZX Spectrum, a modern GPU, and even the most powerful of supercomputers. I would argue that this is actually the simplest possible microprocessor design. The number of states, the size of the memory, and the data bus width may change, but the overall machine organization is the same. It doesn't really matter what your design looks like. If it can emulate this machine, then it's said to be Turing complete. You might be wondering, how on earth is this a microprocessor, and how can it run something like Z80 machine code? Well, in another playlist, I built a machine almost exactly like this, except I've simplified the data bus to have only 2 bits. I assign 4 symbols to these 2 bits. 00 is underscore, which is also blank. 01 is the digit 0. 10 is the digit 1, and 11 is the dollar symbol. Again, you're probably thinking, well, I still don't see the connection. In that playlist, I used this machine to emulate a 6502 microprocessor, and here's the trick. We have the visible 6502 registers, and I've added in a bunch of hidden registers not seen by the programmer. First, I lay out all the registers on the 1D tape. Then next, I lay out the 64 kilobytes of main memory the CPU can address, 1 bit at a time. These 8 tape locations are for memory address 0, 8 for 1, and so forth. After that, I designed a large state machine that manipulates the data in these registers to emulate the execution of the 6502 microprocessor. This took about 2,500 states or rules. Interestingly, it actually took about 5,000 states to make the sequential access memory appear like a random access memory to the 6502 state machine. The nomenclature can be a little confusing. The overall Turing state machine is made up of multiple smaller state machines that can jump to various states within each other. Unfortunately, each smaller state machine is also called a machine, so just be aware that when I refer to different state machines, they're all still part of the same overall state machine. I hand-designed the small state machines that make up the overall 6502 state machine, and they all ended up resembling microinstructions. This particular one is from a slightly different version of the machine, but it copies the data from the data bus register into the X register variable. Let's say the 6502 state machine wants to perform a main memory write. It copies the address into these tape locations, and it copies the 8-bit data here. The memory state machine then copies this data bus value into the main memory byte pointed to by the address bus. You might already be starting to spot the problem with this. Each byte has $1 in front of it. Each block of 256 bytes is called a page, and there's an extra $1 per page. Say I want to write to location FFFF in hexadecimal. First, I mark the start of the FF00 page. This requires about 1 million clocks. That is, FF00 hex is 65280 bytes, times 9 memory cells per byte. Then I need to multiply it by 2 because I have to go there and back. This is a total of 1,175,040 clocks. But remember, each 256 byte page has another $, symbol, so we need to add another 512 steps to this tally, but let's just call it 1 million. Add another 1 million to mark the byte within the FF00 page. then yet another million to transfer the write data. We're up to 3 million clocks so far, and that doesn't even include the instruction fetch in the first place, which may take just as many clocks. In fact, on average, for Apple II Pac-Man, each 6502 instruction required about 3 million clock cycles. It may be crazy to emulate a 6502 using a simple Turing machine, but it is possible, and that's the point I'm trying to make. If I can emulate a 6502 this way, I can also emulate a Z80 this way. I want to modify this machine to make it faster, and here's probably the most important point of the video. Everything I do from now on is about making the machine faster and more efficient. It doesn't change the underlying computation that the machine's capable of. First of all, I don't really need to stick with sequential memory access, provided I can still make it look like sequential access memory to the finite state machine if I want to. Let's change this up-down counter into a simple n-bit register, let's say N8. So the first question is this still Turing complete? i.e., can I emulate a sequential access memory with this? I would argue no, but others may disagree. Don't worry too much if you don't follow the details of this next bit if it's the first time you're hearing it. I just want you to keep your eye on the higher level picture. To emulate a sequential access memory, I need to keep track of my location on the Turing tape. So what I can do is set location 0 in the memory to be the Turing tape pointer, and the number stored here is the location of the read-write head. The finite state machine reads this value, increments or decrements, stores it back in the memory at location 0, and writes the value into the address register, say location 36. The finite state machine then reads the data at location 36, let's say it's A9, and it writes back F0. But it also writes 0 into the address register and remembers in the state variable whether to move left or right. The cycle then starts again. For each original state in the state machine, I now need 2 additional states, one to move left beforehand and one to move right beforehand. Hence, the overall state machine needs to be 3 times bigger than the original state machine. We certainly can do some computations with this. It's actually the basis for the digital alarm clock that I'm building in another series. Indeed, this is the prototype for the alarm clock with the exact same architecture. But the main problem is that the memory size is limited to the size of the data bus. An 8-bit data bus gives us 256 memory locations. Now, that's plenty for an alarm clock or a calculator, but it's not enough for a full computer. We might have some wiggle room if we store some extra address bits in the state variable, but the memory size is going to be very limited. At a bare minimum, there needs to be at least one EPROM entry for every static memory address, so this means the EPROM will always be larger than the static RAM. According to Turing's definition, the configuration should be finite, but the tape should be infinite. This is the reason I would argue that this machine isn't Turing complete. If there are other arguments or counter-arguments, I'd like to hear them in the comments. Okay, I'm going to keep this static RAM, but I'm going to make it a bit smaller. In fact, I'm going to limit it to 64 bytes. I'm going to use half of this space to make a 256-bit Turing tape pointer, and I'm going to add in 32 octal D-type flip-flops, where each flip-flop mirrors one of the Turing tape pointer bytes in the static RAM. This basically means that the Turing tape pointer, which is half of the static RAM, is available on 256 parallel wires. When I want to do a read from the static RAM, the data goes from the static RAM to the finite state machine. But when I want to write to the static RAM, the data goes from the finite state machine to the static RAM and to one of the corresponding octal D-type flip-flops. Now I'm going to add in God's awesome static RAM, which has 2 to the power of 256 bytes of storage. Let's see, 2 to the power of 256 bytes is equal to 2 to the power of 259 bits, which is approximately equal to 10 to the power of 78. Now estimates vary, but the number of atoms in the known universe is in the range of 10 to the power of 78 to 10 to the power of 82. This memory is large enough to have 1 bit for every atom in the known universe. There is some overhead in updating this large Turing tape pointer. I need to be able to increment or decrement the entire 256 bits of the Turing tape pointer, which means my state machine in the EPROM needs to be about 64 times bigger than I had before, or I could lose 6 bits of state. For all intents and purposes, a memory with 2 to the power of 256 bytes is effectively infinite, and it only took 32 octal D-type flip-flops and a 64-fold increased size of the EPROM to achieve this. The point being, for a finite increase in hardware, we can effectively address infinite memory. That's why I would argue that this machine, with the addition of this bank of registers, is Turing complete and can emulate any other computer, including the Z80 inside a ZX Spectrum. A memory the size of the universe doesn't exist, and the ZX Spectrum only has 64 kilobytes of addressable memory, so we only actually need 2 registers for this memory system. These registers are called the memory address register, and I'll label them MAR high and MAR low. All of the control signals for the memory address registers and the read and write signals are programmed into the EPROM in the finite state machine. Providing random access into the static RAM makes a huge difference in performance. We go from about 3 million clocks per 6502 instruction to an average of about 10, which is in the ballpark of the actual 6502, which is about 2.5 clocks per instruction. Here, this architecture is playing 6502-based Apple Pac-Man in real time. Hopefully, we'll be able to do the same thing for the Z80 and the ZX Spectrum. This means our Turing tape pointer is only 16 bits now. This pointer counts up or down by 1 per clock cycle, but I need something slightly different. So, I'm going to relabel the Turing tape pointer to be the program counter and change the rules about how it operates. Technically, this is a program counter variable rather than a program counter. By default, it counts up by 1, but I'm going to let it increase or decrease by up to 128 places in each clock, and I'll even let it take on an entirely new 16-bit value when desired. The program counter variable is great for stepping through code, but I also want to be able to read memory locations without upsetting the program counter. For this, I'm going to add more variables into the static RAM, specifically a 16-bit effective address variable. The state machine then gets to decide whether the program counter or the effective address is copied into the memory address registers. We can even add more variables into this memory, such as an A register, a flag register, and hopefully you can see where I'm going with this. Does this change from Turing tape pointer to program counter change whether the machine's still Turing complete or not? Well, sometimes yes and sometimes no. What we need to be able to do is show that once we've implemented the entire Z80 instruction set, that we can write a program which emulates our initial Turing machine. If we can emulate a Turing machine in Z80 machine code, then we're still Turing complete. I tend to call the top memory the notepad, although technically, the top memory and the bottom memory together are required for Turing completeness. But it turns out that the finite state machine never needs to access both memories at the same time, and we certainly can't read them at the same time because they're both connected to the same data bus. I can actually combine these two memories into a single static RAM device. My device of preference is the 628/128 128 kilobyte static RAM. 64K is for main memory, and 64 bytes of the remaining 64K is for the emulation variables. There's actually an interesting learning point here. I would argue that this machine isn't Turing complete, so this isn't a computer, but this machine is Turing complete, so it is a computer. The main difference is this pair of registers which provides indirect addressing into the main memory. As it so happens, according to this paper by Rojas, a machine requires either a conditional branch instruction or indirect addressing to be Turing complete, not necessarily both. Just a subtle difference on its face, but obviously a major one from a functional perspective. This is the schematic for the memory interface. If you look at the notepad registers on the left, you can see that I've zero extended this out to 16 bits. Then in the middle, we have the memory address registers, which combined are also 16 bits. This feeds into a single 128 kilobyte static RAM. The notepad address comes from the state machine, as does the W bus. I'm going to start wiring up the memory address bus, which is highlighted here in blue. Later in the sequence, I'll wire up the W bus, which will be the red wires. This may be very new to some of you watching this, but just while I'm doing this wiring, I'll speak about my journey and how I got here. In undergrad, I was actually taught CPU design by one of the top Australian computer scientists, Professor Chris Wallace. He invented the Wallace tree multiplier and he even has a 7400 series chip named after him, the 74275. Anyway, I was taught about Alan Turing and Turing machines in a different subject, Foundations of Computers, which was actually taught at a different year level. And at the time, I never really understood the connection. They were in different silos in my brain. Moving forward, I did a PhD, but that was on computer graphics architecture optimized for virtual reality, and I wasn't really looking at CPU design. Later down the track, I joined Interval Research, which was Paul Allen's private research lab, which was meant to be modelled after Xerox PARC. I was mainly working on a low latency virtual reality project, but there was an internal rule that said we had to spend 30% of our time on another project, which in retrospect is actually a very clever rule for a research lab. Anyway, the second project I worked on was about natural computing. It was a much more blue sky project, but it was about how the fundamental nature of computing could be applied to emerging technologies such as FPGAs, which were quite new at the time, and we even looked at quantum computing. This project really planted the seed of interest in me for the link between theory and architecture. Then, a bit further down the track, I got involved in life sciences, and the DNA molecule was an obvious platform for computing, and that's when I doubled down on understanding this link between theoretical computer science and computer architecture, which ultimately led to this YouTube channel. There's still some detail I need to go over for the timing and data transfer between the memory system and the finite state machine, but I think I'll go over that in the next video. This is enough for now, but I would encourage you to download the 1936 Turing paper. It's long, but just read the first 3 pages and try to correlate it with the designs I've shown in this video. If you can do this, you'll be a long way down the road to understanding the fundamental basics behind how microprocessors work. In the next video, I'm going to build a graphics system and go over all the timing and control signals.